Record this one because I've had two other classes I haven't had a chance to record it. So here we go. We're recording this one. So we're looking at Dalton's law of partial pressure, and we're going to see that the pressure total is equal to all the pressures added up. Our example here in our diagram is I have a pressure of helium at 1 atmosphere. In my other container, I have a pressure of nitrogen gas at 1 atmosphere. And in my third container, I have the pressure of oxygen gas at 1 atmosphere. If I were to push all three containers into one container, I will see that my total pressure is now 3. Why? Because 1 plus 1 plus 1 equals what? 3. So let's do a couple word problems to help us see this. We're going to do the first example together. Okay. So we have a mixture of oxygen, hydrogen, and nitrogen gas. And they give us a total pressure of 278 kilopascals. So I got P total equal to the pressure of my oxygen gas plus the pressure of my hydrogen gas plus the pressure of my nitrogen gas. And I'm told that the total pressure is 278 kilopascals. Now I'm told that the partial pressure of the oxygen and hydrogen are 112 kilopascals and 101 kilopascals respectively, meaning that oxygen has 112 kilopascals, so 112 kilopascals oxygen, and my hydrogen has 101 kilopascals plus 101 kilopascals hydrogen. I need to figure out what is the partial pressure of the nitrogen in kilopascals. How would you solve for this problem? What was that, Jesse? All right, I add those two up. That gives me what if I add those two together? 213. I'll go with you. So 213 kPa equals 278 kPa plus my unknown kPa. What do I do after that? Yeah, I'm subtracting 213 from both sides, right? So that's going to give me a answer of pressure, partial pressure of nitrogen gas to equal, pull out my handy dandy calculator, 278 minus 213, boom, gives me 65 kPa nitrogen gas. If you can add numbers together, you can do partial pressure laws. If you can subtract things from each other, you can do Dalton's partial pressure laws. So to make things a little easier, I'm going to use my other sheet here because I kind of wrote over my next example. So let's go ahead and take a look at the second thing that Dalton's law tells us. A common method of gas collection in a laboratory is the collection by water displacement. The gas collected will not be pure because it's over water, and we know that our kinetic energy is the average energy that our molecules are moving. So some are already going into the evaporation state just from existing. So if I'm collecting gas over water, I'm never going to have an exact pure sample. But I can measure out how much of the gas is just the thing I want to collect with finding out what is the total pressure that I collected and subtracting the kPa of my water temperature. To determine the pressure of the dry gas alone, we subtract out the pressure of water vapor. In this form, the formula that we use looks like this. Pressure of the dry gas equals the total pressure minus the pressure of the water vapor. So we look at the back page. We have our second example. Example number 2. A sample of hydrogen gas is collected over water at 14 degrees Celsius. The pressure of the resultant mixture is 113.0 kPa. What is the pressure that's exerted by the dry hydrogen alone? Pressure of the dry is equal to the total pressure of the system minus the pressure of the water vapor. Now I know that the total pressure is 113.0 kPa. I need to use the chart on the front page to figure out what is the pressure of the water vapor that's also in the gas as well. I'm looking at 14 degrees Celsius. So I'm on my chart here. I find 14 degrees Celsius. I see that the water vapor pressure is 1.6. So 113.0 kPa minus 1.6 kPa. If you're not given the water vapor pressure, you will be given a way to calculate it, mostly through a graph table. So let's take out my calculator. 113.0 minus 1.6 equals 111.4 kPa. Is that my final answer? What's my rule for sig figs? I'm adding and subtracting things. Is it number of sig figs or is it least amount of decimal places? Was it? Which one is it? Is it least sig figs or least amount of decimal places? Not sig figs.
Decimal places.
Decimal places. When I'm adding and subtracting, it's least amount of decimal places. When I'm multiplying and dividing, it's the least amount of sig figs. So be careful with which one you're using. Let's look at question 1 together, and then we'll have you do questions 2 through 6 by yourself, and we'll come back and we'll take a look at what you did. So, a mixture of neon and argon gases exert a total pressure of 2.39 atmosphere. The partial pressure of neon alone is 1.84 atmosphere. What is the partial pressure of the argon? So, I got pressure total equals partial pressure of my neon plus the partial pressure of my argon. And I'm told that my total pressure is 2.39 atmosphere. And the partial pressure of my neon alone is 1.84 atmosphere minus my unknown. How do I solve for this? What? I didn't understand what you said there, Nana. Oh, subtract 1.84. Yes. subtract 1.84 from both sides, right? $2.39 minus 1.84 gives me what number? What's my final answer? 0.7? Yeah, 0.75. I got 0.55. I want you guys to work on questions 2 through 6 by yourself. Because I'm recording, I want to make sure that everyone's got the homework here. That's the Unit 9 review. You need to bring this back to me completed, as it's worth 10 points. So a hefty homework for a hefty bit of work that you're going to have to do. But I'm going to put a timer on the board. Well, I don't know if I can put a timer on the board if it's going to mess with my recording. It's not. Perfect. Now I have a timer for us on the board. I'm going to give you 7 minutes. I want you to work your problems 2 through 6. Down to 12 real fast.
It's like you go look at the chart, you find 12, and you find total. So that's what you have. Your assignment. I don't know if you're not to my knowledge. I don't know about the
With that, you need to make sure you're doing all 5 questions of the homework right now. So if I'm looking at number 2 here. So I have a 450 milliliter sample of hydrogen is being collected over water at 12 degrees Celsius. Now the pressure of the hydrogen and the vapor is my 78.5 kilopascals. We need to figure out what is the partial pressure of just the dry hydrogen. So what do? I grab my handy dandy my dry equation. My pressure of my dry is equal to the pressure of total minus my water vapor.
Hello, duck hunters. If you think that you have the most ducks, please come to the front office immediately after dismissal. The top 3 duck hunters will win a prize. Happy Friday and have a great weekend.
So if I have my table here, I'm looking for 12 degrees Celsius. 12 degrees Celsius gives me a water vapor pressure of 1.4 minus 1.4 kPa. So it's going to equal out to 77.1 kPa is my dry hydrogen. Number 3.
But you don't have to do anything like with the paper, like my decimal place or anything like that.
No, it's decimal places. 1 decimal place, 1 decimal place. Therefore, my final answer will only have 1 decimal place. So I have 888 milliliters of oxygen being collected over water with a temperature of 27 degrees Celsius. The total pressure is 55.8 kilopascals. What is the dry gas of oxygen? P dry is equal to my total, which is 55.8 kPa minus, pull up my table again, looking for 27 degrees Celsius, 3.6. If that's the case, 5.8 minus 3.6 gives me 52.2 kPa for just my gas. Carlos, could you open the door for us, please? I appreciate you. So I have a metal tank that contains 3 gases. In those 3 gases, I have 35 atmospheres of oxygen gas. I have 5 atmospheres of nitrogen gas. And I have 25 atmospheres of helium gas. What's my total? 65 atmosphere when I add everything up. 35 plus 5 is 40. 40 plus 65 is 65. 5 and 6 are tied together. Blast furnace gives off many unpleasant and unhealthy gases. So I have a air total of 99 atmosphere is equal to total air pressure is 0.99 atmosphere. The partial pressure of carbon dioxide is 0.5 atmosphere CO2 plus, and the partial pressure of hydrogen sulfide is 0.02 atmosphere H2S. And then I need to figure out what is the partial pressure of everything else. How do I solve that problem?
They add the
Yeah, but I add these 2 together, so that's going to give me 0.07 atmosphere, right? What am I going to do with that number? Subtract from both sides. So that gives me 0.92 atmosphere is equal to everything else. Now, question 6 is directly tied to question 5. So, if the air from question 5 contains 22% oxygen, what is the partial pressure of oxygen near the blast furnace? Now, am I going to use the 0.99 atmosphere number, or am I going to use the 0.92 atmosphere number? We use the 0.92, right? Because the 0.07, that's the carbon dioxide and the hydrogen sulfide. They're not part of everything else. 0.92 atmosphere times 22%. Can I do that? I got to convert my percentage into a decimal first, right? And I can do that by dividing it by 100. And that gives me 0.92 atmosphere times 0.22. 0.92 times 0.22. How many sig figs am I going to have? 2. Because I'm multiplying, right? 1, 2, 1, 2. Therefore, my final answer is going to be 0.20 atmosphere is oxygen. Had to think a little bit outside the box to get that last one, but if you can add things together, you can subtract things from each other, you know you can figure out Dalton's partial pressure laws.